Hi, this is Olivia Stodig, and this is the second video covering the updates of the parametric box model code in version 003. So on the last video, we covered the first two topics on the slide. So we checked the analysis results from our parametric study. We did some model modifications, and we also talked about some additional features which allow us to model a multi-section wing with core-filled sections. In this video, we're going to cover the design optimization topic. So we're going to look at a very simple example using OpenMDAO and SciPy. And then we are actually going to apply this optimization approach to our wing model. Okay, so to get an introduction to OpenMDAO, probably the best is to look at this website. You will also have some additional resources that cover optimization in general in there. And for this video, I think the best approach is probably to just jump straight in and to cover the paraboloid optimization example. So if we have a look at that, you can go to the OpenMDAO documentation, and you will find this page. In here, you have the basic user guide. And the second topic in there at the moment is this paraboloid simple discipline model. You can, of course, just implement this script exactly as it is. We've actually modified it a little bit in our own script, as I'll show you in a minute. But the equations that we implement are exactly the same. So here we have a paraboloid analytical equation that has a known minimum at x equals 6.6667 and y minus 7.3333. And we are going to try and optimize this to a minimum value from a random starting point. So this is the description of the model. And if you go to the next section here, which is the optimization of the paraboloid, there's also an example in the documentation of OpenMDAO how you can implement that. And again, we've based this example that I'm going to show you around this code. Okay, so as I said, yeah, OpenMDAO is a free open source library, so you can actually just copy or clone the directory on GitHub. And it has a large user community. It's currently developed by NASA in the US, and there's a lot of research work that has been using this over the years. So feel free to browse this in more detail. So if we go back to our code, right, so in our directory structure, we have got this parabola optimization folder, and in there you'll find a simple module called design optimization. And this implements this paraboloid optimization example from the OpenMDAO manual with some modifications. So of course, the first thing to do is to import our OpenMDAO module. And then we also want to import, in this case, the SLSQP driver from the SciPy library. So this is actually what we're going to use as our optimization algorithm. And this is a gradient-based algorithm, so it is different from the one that is used in the OpenMDAO example. And the implication of that will be that we will need to calculate some gradients, which I'll cover in a minute. We also, instead of using the approach of the MDAO example, we are continuing with defining our inputs right at the top of the file. So we actually have this input structure here, which allows us to see all of our inputs in one place. So the main definition of our problem includes the components. So here we have a component which is the paraboloid. And in the OpenMDAO example, you'll see that there's also a constraint in the optimization. So this is a simple analytical constraint that we're implementing here on the input variables. Then we have the definition of our input data to the optimization. As we've seen, this is simply a function of the x and y variables. And we set some initial values for these as well, and some bounds. So we say that our input variables can change between -50 and 50. And both of these inputs are to the paraboloid component. Now, because we actually prefer using connections to declaring global variables in our optimization, we are setting up two connections here, which feed the input variables from the paraboloid to the constraint component. So basically, we're just passing x through one component to the next. This might be a little bit of an overhead at this point, but it allows us to define these inputs in a very generic way, which declaration of global variables, such as in the example, is a bit more error prone and potentially complicated when you have larger models. So we are defining these connections, and we can see what the effect of that is in a moment. And then in terms of the output data, we need to declare both the internal outputs from the components and the final objective and constraints. So here we have our the x and y's that we're passing through our paraboloid component to the constraint component. And then we have our objective function, which is our fxy, which comes out of the paraboloid, and our constraint comes out of the constraint component. And again, here on the constraint, we just need to say what the constraint, the maximum and minimum constraint values are that we can accept. Okay, so and finally, yes, we have some optimization options. So here we can set the optimizer that we want to use, the maximum number of iterations, the convergence tolerance. This is about the debug and the display that that is printed to the command line during the execution of the optimization. And we'll see that this is actually quite useful. So by default, nothing is output here, but it is quite a useful thing to look at. Okay, and then the rest of the file structure here is split into the main function, which is executed here as the main module function by calling this inputs 0 vector. And in our main function, we have the flow of execution. So the first thing is here that we define the simulation components. So this is reading the component definition from our inputs and creating additional components by calling this problem model add subsystem method. And you'll see that actually the paraboloid component is defined as a class here. So this is, again, this very similar to what's on the OpenMDAO example. And these components are specific to OpenMDAO. So they have a structure that you need to respect. The main things that need to be in here is the setup partials, and the compute. In our case, the setup is really just to say what the inputs and outputs are to this component. So this is just picking up what we have in the inputs, and we're passing that through by applying this by applying the input component to this class. So this is all the data that's available in the input is available to this component in the setup and in the compute. And here we have the main compute function. So you can see we're literally just picking up our x and y values from our inputs, calculating the fxy output, and then passing through the x and y as an output as well for the constraint. Okay, so once we've defined the simulation components in our first step, we then define these internal connections. And that's using the problem model connect method. We then set up the optimization driver options. So I just mentioned that all of these are specified in the inputs. We also specify that we want to calculate approximate totals for the total finite difference gradients. In this case, we don't have any analytic gradients or other gradients that we can provide the driver. So this is the only method we've got available. And we also then need to define the design variables. So in this case, that's just our x and our y, the constraints and the objective. And finally, we can execute our optimization. So once we get to this point, we run the setup. This is where OpenMDAO actually processes all the inputs that we've given it so far, and it checks that it all makes sense. And it then generates this N2 diagram, which allows us to visualize the flow of the data within the optimization model. And then it executes that flow by running the driver. So here we have a very simple post-processing, which is just printing the output values at the end of the optimization. So let's run this. So we can execute this again simply in the debug session. And this might take a little bit of time. Okay, so the first thing that we've just seen here is that it's actually generating this N2 diagram. And then in the background, we should see that it is running the optimization, and that actually already completed. So right, so we can have a quick look at the N2 diagram first. So this is you can save this as an HTML file. It is showing you the inputs at the top to our optimization model, and it's showing us one iteration of the model execution. So we can see we've got the inputs at the top, and then we have our fxy, which is one of our outputs, is our objective function here, and we've got our g, which is our constraint at the bottom here. And you can see that these arrows indicate how the data is passed into these different function evaluations. So we have our main inputs x and y here at the top. And these are obviously used in our paraboloid component to calculate our fxy, but they're also passed through to our constraint, and the same thing in our constraint component. So that's this marked out by a square down here. We have our x and y inputs, and these are used to calculate our g value. So this can be quite useful to understand how your different components and inputs and outputs are connected. So here we can see the output from our optimization, and we have got 2 iterations, and we have the debug output here, which allows us to see what the value of the variables was at each iteration, the value of the constraint, and the value of the objective. And we can see that in the first 2 iterations, we don't actually get a change, so it's staying at the same inputs. That's the usual behavior of the SLSQP driver, and it's actually calculating the total derivatives here in this step. And then our second iteration, SLSQP2, which is actually our 3rd iteration, it actually then it comes straight down to where our minimum is, or within the tolerance distance. So it actually converges really, really quickly on this one. So it only took 2 iterations and 2 function evaluations. That's not counting the additional function evaluation at the beginning. And it found these optimal conditions at the end. So our objective of -27, constraint value converged 10 to the -10, and our variable x and y values at the optimal design position. Okay, so this is our simple paraboloid optimization example. And if you can run this, then the next step is to move on to our Wingbox or wing optimization, which is here in our main file under design optimization.py. So if we look at this file very quickly, you will see that it is very similar in terms of the structure. Again, we're importing our OpenMDAO and SciPy libraries here. And we're also importing our parametric box library as Parabox. Okay, so just to define our optimization problem that we actually want to implement. Of course, you could optimize a large number of different things with a wing model like this. Here, to keep it simple, we want to simply minimize the wingtip rotation, so this RY rotation that we output at the tip of the wing. And that means that we're actually going to maximize the deflected wing washout. So we want to make this angle at the tip as negative as possible, starting from an undeflected shape that has no twist on the wing at all. And in terms of the constraints that we apply, we want to have a fiber direction rotation angle, which varies between -50 and 50 degrees. And we want to have a wing tip vertical deflection that is smaller or equal to 6 centimeters. So this is arbitrarily, we decide we don't want this wing tip to deflect more than that. Okay, so if we have a look at how we've implemented that, in this case, we only have a single component in our optimization, which is called Parabox. And if I just minimize this quickly, and we can see that we have this Parabox here implemented as an OpenMDAO explicit component, as we did with the paraboloid example just before. So again, we have this setup here. We have the partials, which are, again, we don't feed it any analytical partials, so this is just finite differencing. And we compute our deflections using, in this case, we're calling our main Parabox main function. So this is doing exactly what we did in the parametric study, except that now we are feeding this data. So we're getting our inputs from the optimizer, and we're feeding our outputs, so our UZ and our Y, we're feeding that back to the optimizer as well. Okay, so in terms of our inputs, again, very simple. In this case, we have a single input, which is our rotation angle for the main fiber orientation for the composite materials. And we start this off at an angle of -20 degrees. So if we remember our parametric study, this means that we probably will get some wash in at this point. So we will get some positive RY rotation. And we set our bounds here on the maximum and minimum rotation input values. We have no connections in this case because we only have one component. And the output data that we're interested in is our RY objective. So that's our objective function and our UZ constraint. So again, the value doesn't really matter on either of these because they're calculated by the optimizer. But on the constraint, we want to set what our maximum and minimum expected deflection should be. Okay, and then here on the optimization options, we set options that are very similar to what we used just before. We've added an additional option here, which is allowing us to switch the N2 diagram on and off, because it can be a bit annoying if this always pops up. Okay, and then here in terms of the steps, this is very similar to what we've seen before. So we define our components, we define our connections, our driver options, our variables, objectives, and constraints. Here's an additional step that we didn't have before. So this is a bit, this is interesting for this model because it's a bit more complicated, and we don't actually want to rerun this, all the analyses after we've done the optimization. We still want to be able to access the output of these analyses on a case-by-case basis. So this is why we're attaching a recorder to this optimization, which allows us to record all the inputs, outputs, and gradients. So record the derivatives of our optimization. analysis functions. Then we execute our optimization. So this is the same that we had before, and we have some basic printout. Now on top of this, we've also got a post-process function, which I'll explain in a minute, is actually very useful, as I said, once you've got this recorder, which is actually an SQLite database. That will stay after the optimization is completed, and you can rerun this post-processing function on this database at any point afterwards to plot your results in different ways. So let's see what this looks like. So I'm going to launch this and then probably speed up because it takes a little bit of time to run. Okay. So we will, or we might just have a look at the N2 diagram as this comes out. I think I switched it on here. Yep, that's fine. Okay. Okay, so this is our N2 diagram. So much simpler actually than our example from just before. So we have a single input, which is our angle, rotation angle, which is fed into both our RY and into our Z, UZ calculation. The RY being our objective, the UZ being our mode constraint in this case. And that's it. So this looks pretty straightforward. It looks like our model has been defined correctly, and hopefully it should be running in the background. Right. Okay, so see you in a minute. Okay, so our optimization just finished. So we've got the optimization terminated successfully message that comes out here at the bottom. It took quite a few iterations and function evaluations. So depending on your computer, this might take 5 minutes or a little bit longer. We've got the final optimization output here at the bottom. So we have an RY rotation value of just under 0.04 radians. And that's a few degrees negative rotation at the tip of the wing. And we've got a constraint value which is very, very close to the maximum that we've set, which was 6 centimeters. So here we are very close to that. And we have a optimal rotation angle of 22.68 degrees. Obviously, depending on the tolerance that you set and so on, this might change a little bit. Just be certain that you do converge. So if you set a tolerance that's too high, I think the default that I had before, the 10 to the minus 6, wasn't sufficient to converge this. So you will have to set this to a lower value. So I think I set it to 10 to the minus 8 here to get to this point. And again, this is a function of your problem and a function of your input variables as well. So let's have a quick look as well at the post-processing. So I haven't shown you the code yet, but if you just execute this function, this optimization, you will see that it outputs some plots at the end. And this is plotted from the recorder file. So we can see in these plots just the major iterations. So that's on the x-axis, we've got 14 major iterations. So these are iterations where the gradients were calculated. In between of these iterations, we have some line searches, which are not plotted here because they would confuse the image. And here we can see that starting from our starting point of minus 20 degrees, our variables slowly increased and then increased very rapidly and then switched back to about 22 degrees. So very constant in the last 5 or 6 iterations here. So this is a good sign to say that we've probably converged on something. And if we then look at our optimization objective function, here we have a very nice evolution. So it's very slow initially as well, which corresponds to a change in variable, which is very small initially. And then as soon as we go into negative angle rotations for the material, we also then see this bend twist coupling, so this negative bend twist coupling kicking in, and we have negative rotation angles, and it converges again towards a constant value here, towards minus 0.04 for the later iterations. And then finally, this is our constraint function. So we can see now that this is actually driving our optimization. So we have the constraints initially are not active, but as soon as we then switch into our negative rotation angles, and we initially have a very large rotation angle of 40 degrees, where our constraint is very much exceeded, this is where the optimizer cuts back and goes and then goes back to a smaller variable value, which corresponds to a value which is much closer to our constraint of 6 centimeter vertical deflection. And we can see that this constraint is fully active in these last six iterations, which is constraining our problem. So we found here our minimum rotation subject to a constraint on the vertical deflection. Okay, so if we stop this now, we can look at our script again. And the post-processing function, you can have a look at this in more detail yourself. There's all the explanations in the OpenMDAO documentation as well regarding the case readers and the cases. But very, very simply, this is a SQL database that you can now see. If you look in your file structure, you should have an SQL database here, which you can save. It's a binary code, so you can't just look at it, but you can interrogate it using the SQL reader. So if I go back to optimization, so post-process. So all we're doing here is we reading this database and then reading the cases from that database. And these cases, let's see if I can have a look at the structure. So if I just comment out our main function here, it should hopefully work. So we're not actually going to rerun our optimization. We just want to post-process this file and stop it in, let's say, inputs history. Okay, so we want to extract one case and look at that. So let's stop it here. So if I just look at my debug session at the same time. Okay, so we can see that we've just loaded this database up. So no optimization happening here. So we have got our inputs, we have our driver cases. So if you want to look at that, you can see all the iterations that our optimization did previously, our 30 function evaluations. And one of these function evaluations corresponds to this case. So this is our first case. And we can see that we have several outputs here. So our RY, RZ, and our angle. And then for the major iterations, you will see that there's some additional output here, which corresponds to the derivatives. So that's it really. Of course, yeah, once you have this data, you can process this in any way you want. We just have a simple plotting function here. But you could use it in many different ways. So that's covering our wing model design optimization. So we have implemented this, and I hope you enjoyed this video. Thank you.